plan for today is to do this example you have here in the whiteboard. So basically you have a beam with a concentrated force of 20 kilonewtons at point B, a concentrated force of 30 kilonewtons at point F. Then you have that rectangular distributed load over there, 10 kilonewtons per meter. And you have a double support at point D and a simple support at point G. Okay? And this is the plan for the lectures today, to solve this example in two different ways. The first one is same way like we learned last week. Okay? Just doing section by section of the beam, cutting the beam, dividing the beam into parts, and then getting the shear force equations and the bending moment equations for each section of the beam. And the other method we are going to learn today is the Mcculloch bracket method, which we are going to see how to use that method, which has the great advantage of Mcculloch bracket method is that you only need to cut the beam one time only. For example, in this example, we are going to start using the method we learned last week. So we will have to cut the beam 1, 2, 3, 4, 5, 6 times, right? Because remember from last week, every time the load is changing, we need to cut the beam again. In the Mcculloch bracket, I'm going to show you today that you only need to do this one time. So there is a huge difference on the speed you can get your bending moment and shear force equations. Okay? But in order for you to see that, and also in order to practice a little bit these exercises, we will start by doing this example with the method we learned last week. Okay? So, what we have to do is to start cutting the beam. So we start in section AB. So I'm going to cut my beam on this section AB. All right? And then I'm going to look to the left side. And this is going to happen if I do that. So if I cut the beam there between point A and point B and look at left side, I will have point A here. That's all I have, right? And then, of course, I need to have my shear force, Vx, and my bending moment, Mx. Right? And of course that my x coordinate, you remember we introduced this local coordinate x, in this case starting with origin at point A and going all the way until the point where we are cutting our beam. Okay? So you remember this shear force V and bending moment M that we did this last week, that are basically the internal force and moment we have on the beam that will restore the equilibrium, right? Remember that? And in this case, so this is all we have when we cut our beam with this section and look at the left side. This is everything we have, right? We don't have any force on the left side of my beam. And then if I write the equilibrium equations, summation of forces in the y direction equal to 0, we will get what? We will get minus Vx needs to be equal to 0 to be in equilibrium, isn't it? So basically we don't have any transverse shear force. And if I do summation of moments about the point where I am cutting my beam, this summation of moments needs to be equal to 0 to be in equilibrium. The only moment I have is this moment mx, right? And so in order to be in equilibrium, this mx needs to be equal to 0 in this region of the beam. So this is quite easy in this section, right? So these equilibrium equations I'm using here, they correspond to this free body diagram, not the entire beam that I have there in the top, right? I'm doing the free body diagram when I cut my beam in between point A and point B, looking at left side. So this is my free body diagram, not the entire beam. So careful with that. Okay, so we can start building our. So I'm just going to copy this. We can start building our diagrams. Right? I can draw something like this. So basically I will have to build my shear force and bending moment equations in all these sections of my beam. And I can say, for example, here I'm going to plot my transverse shear force, Vx. And here below I'm going to plot my bending moment, Mx. Okay? All right? And for this first region, between point A and point B, we saw here that we have a transverse shear force equal to 0, a bending moment equal to 0. So basically we have something like this here, right? That one was really very easy. Okay? Now, we can continue our analysis. So what do I have to do next? What do you think what do I have to do now to continue my analysis? Between B and C, so I need to cut my beam now between point B and C. So I need to have a section plane or a cutting plane between point B and C. And again, look at everything I have on the left side, right? So I need to look at all of this that I have on the left side of my cutting plane. And I need to do the free body diagram of that part of the beam that I have inside that red circle, right? That's what I'm going to do. So I'm just going to draw here between, so we have here this force of 20 kilonewtons. Right? So this is my point A. From here to here is 1 meter. I'm just going to put like this in green. It's 1 meter. So this is my point B, right? Okay? And now, again, because I'm cutting the beam between point B and C, so in that cutting section, I need to include my transverse shear force, Vx, and my bending moment, Mx. Okay? And again, this is my x coordinate, which goes from point A all the way until the section where I am cutting my beam, somewhere between point B and C. And now this is another free body diagram. So this is a new free body diagram. This one here you have inside this circle in blue. And then we need to write the equilibrium equations for this free body diagram. And it's always like this, right? Okay, so if we do that, so this is my free body diagram. So I need to have summation of forces in the y direction needs to be equal to 0. So it means I will have what? Minus 20 minus Vx. That's all I have, right? In the vertical direction. So this needs to be equal to 0 to be in equilibrium. So it means Vx needs to be equal to minus 20. Okay? And now the other equilibrium equation I have is summation of moments about the point where I am cutting my beam needs to be equal to 0. You tell me? Yes?
Shouldn't Vx be acting upwards?
Only if you look to the right side of the beam, it needs to be upwards, yes. But when you look at, when we did cut here, right, with this section, we look at the left side. When you look at the left side, it needs to go downwards. If you decide for some reason you want to look to the right side of your beam, all of this, then it needs to go upwards. It's a kind of a convention, okay? I showed you last week why. Why is that? Okay, you tell me then, the moments. Which moments do I have? Mx. What else? Sorry? Plus 20 times what? X minus 1. Yeah. Yeah, that's it. Very good. And so it means Mx is going to be equal to 20 minus 20x. We can say something like this, right? I just sent that to the right hand side. I changed the signal. So these two equations we need to have these two equations. Why? Because now I will just copy. So if I take Vx and paste it here, so we have between point B and C, we have Vx equal to minus 20. So, and constant, right? Minus 20 and constant. So we can say that between these 2 points, I will have something like, a constant distribution, and this is equal to minus 20. All right? Isn't it? Now, for the bending moment, I will copy this. I will paste it here. So we have this equation for the bending moment. Mx equal to 20 minus 20x. So, look, it's a linear function in x, so it means it's equation of a line. So if I have 2 points, I can then draw this line. And then one point I can have is point B, right? I can have this point B here, which corresponds x equal to 1, right? X equal to 1 is point B. So if I replace here in this equation x by 1, I get 20 minus 20, I get 0. So basically I get this point here, right? 0. You agree? And the other point I need now is point C. C corresponds to x equal to 2. If I replace here x by 2 in this equation, I get 20 minus 40, which is minus 20. So this means I will need to have here this point minus 20, right? And then I just need, if I connect these 2 points with a line, this will be my distribution of my bending moment, right? Okay, you see? So, transverse shear force, constant, equal to minus 20. Bending moment is a linear, and this is the distribution, is 0 at point B and minus 20 kilonewton meters at point C. Okay? So we need to move now to the other region of the beam. Okay, so I will copy this. I will paste it here. And what do I have to do now? Between C and D, so I need to cut now my beam between point C and D, and we are going to look again to the left side of the beam and do a free body diagram for this left side of my cutting plane. Okay? And then if I do that, I will have 20 kilonewtons here. I will have a little bit of my distributed load, right? So this is still 10 kilonewtons per meter. So this is my point A, point B, point C. Right? You agree with me? What else do I have? What else do I need to have? Sorry? Internal forces. Yes, I need to have my internal force Vx. And I need to have my moment as well. Mx. Okay? Again, my x is starting at point A and going all the way until the section where I am cutting my beam. Make sense or not? Always like this. So now we have a distributed load. We need to be careful with that. So let's do this. So this is my free body diagram now. Maybe we can put dimensions here, 1, 1. So this is x, so this is 1 and 1 here. 1 meter, and from here to here is also 1 meter. It doesn't look like, because I didn't draw this on scale, but it is 1 meter, right? So if you want, we can do something like this. So this distance from here to here is going to be how much? X minus? Minus 2. Yes, very good, right? So we can leave it like this. So you understand what I mean with this. So we have all the distances we are going to need for the moments, right? Calculate the moments. And now we can write the equilibrium equations. Summation of forces in the y direction equal to 0. You tell me. Sorry? Minus 20. What else? Minus Vx. Anything else?
Distance from A to X would be 0.5x plus 1. 2 plus x minus 1 over 2. X minus 2 over 2.
What distance?
5x plus 1.
No, but for the forces. We are doing the equilibrium equation for the forces in the vertical direction, not the moments yet. That will be for the moments, right? Yeah, for the forces, what I need to have, look, this is important. For the distributed load, I need to have an equivalent force, which basically is equal to the area of this rectangle that I'm doing here in blue. The area of this rectangle is going to give me my equivalent force, my equivalent concentrated force, okay? So that area is equal to what? 10 times x minus... Yes, very good. 10 times x minus 2, right? Is the area of this rectangle. So this 10 kilonewtons per meter is the height of the rectangle. X minus 2 is the width. So the area is 10 times x minus 2. All right? And do we have any other force in the vertical direction? That's it. So this needs to be equal to 0. And so from this equation we get Vx is going to be equal to minus 10x. So we have here 20 minus 20. No. One is positive, one is negative, right? So it's 0. Yeah. So that's all we have, is this, right? Isn't it? Now, summation of moments equal to 0. You tell me, please, which moments do I have? Mx. What else? Sorry? So let's do this one first. Okay, let's do this 20 kilonewtons first. So plus 20 times what? X minus 1. Yes, x minus 1. Very good. And now let's do the distributed load, the moment produced by this distributed load about point X. So we need to have force times distance. Force we have already, right? We did it before. This is the force, right? We all agree this is the force, right? The equivalent force, right? And this equivalent force, we can do something like this. This equivalent force is going to be located in the centroid of this. Let's say this is the centroid. And this equivalent force, we already saw this is 10x minus 2, right? You all agree? And now the distance we need is basically this distance for the moment, right? We need this distance here, from here to here. And this distance is how much? X minus 2 over 2. Yes, that's it. Very good. So, in order to have the moment, I need to multiply the force, which is this 1, with my distance. Then I get the moment, right? Isn't it? So, we can then say that that moment is going to be anti-clockwise, so positive. So the force is 10x minus 2. This is the force. And the distance is x minus 2 over 2. So I can say x minus 2 times x minus 2 is x minus 2 squared. Is okay? Everybody follow this one or not? So 10 times x minus 2 is the equivalent force in the centroid. Then I need to multiply by the distance to get the moment. And that distance is x minus 2 over 2. Then I get the moment. Okay? And that's all we have. So this needs to be equal to 0 to be in equilibrium. And now we just solve this in order to mx. So we are going to have minus 5x minus 2 squared minus 20x minus 1. We can do like this. isn't it?
Would it make sense to expand that?
You can expand, yes, perfectly fine. Now, we can expand that because now we need to plot the diagrams, right? So let's copy the transverse shear force. Copy here and let's paste it here. So this is our transverse shear force. Okay? Minus 10x. So I need to plot this between point C and point D. Don't forget we are doing the analysis for the region of the beam between point C and D. So again, it's the equation of a line again. So I need 2 points. First point is point C. Point C, which corresponds to x equal to 2. So if I replace here x by 2, I get minus 20. So basically I get this point, right? Minus 20. The other point I need now is point D. Point D is x equal to 4, exactly. So if I replace here x by 4, I got minus 40. So it means I will get this point over here, which is minus 40. And then I just need to connect these points with a line. And this is my distribution of the transverse shear force between point C and point D of the beam. Okay? And we need to do a similar thing for the bending moment. So I'm going to copy. So we obtain this equation, right? Let me copy. So now we have a quadratic distribution. So we will have a parabola, right? For the bending moment. But we can have, so we know that we will have a parabola with a negative coefficient in x squared. Look at this. I will have here a negative coefficient in x squared, right? So if you expand this x minus 2 squared, you'll get x squared minus 4x plus 4. So it means the x squared coefficient is negative. So it means the curvature of the parabola needs to be facing down, right? So we can get 2 points again, point C and point D. So if we start with point C, we replace x by 2 in this equation of the moments. If you do that, if you replace here x by 2, you get this term is 0, 2 minus 2 is 0. Then you get what? Minus 20, right? You agree with me? We get minus 20. So it means we will get this point here, minus 20. Okay? Point C. Now if I replace, if I get another point, point D, this point D here means x equal to 4. So you did replace already here x by 4? Okay, yes. Okay, you have here 2 squared is 4, so you have minus 20, minus 60, minus 80, right? Yeah, I agree. So you will have, let me just expand this a little bit more. You will have here minus 80, something like that. And then your bending moment will go from point minus 20 to point minus 80 with a parabola, right? This parabola does not look very good. Let me try to do it a bit better. So you'll go from here to here with something like this. Right? Much better now, right? And this point, don't forget, is minus 20. Okay? You see? Everyone is following or questions? No questions? So I assume everything is all right. And we need to continue our analysis. Let's okay, so you tell me, what do I have to do now? What do you think I have to do now, please? Sorry? So if I cut, find the reactions. Okay, but if I cut in DE and look at the left side, look, if I do this, I have a support there, right? Like the colleague is saying here. So it means I need to get those reactions first. I cannot continue now anymore without getting the reactions first, okay? So that's the next step I have to do, is to get the reactions. And in order to get the reactions, I need to do the free body diagram of the entire beam. That's it. So this is going to be my x-axis. This is going to be my y-axis. Okay? So if I do summation of forces, Oh, before that, of course, I forgot to replace the supports with the reactions. So I'm going to remove this support. Which reactions do I have to put here? Which reactions do I have to put here? So if I try to move this point in the horizontal direction, does it move or not? No. So it means I need to have a horizontal reaction, dx. If I want to move in the vertical direction, it's possible or not? It's not possible, right? So I need to have a vertical reaction. And this support as well, I need to remove this support and replace with reaction. Look, you have some rollers here. So it means the movement in the horizontal direction is possible. So it means no reaction. But the movement in the vertical direction is constrained, which means we have a reaction in the vertical direction that I will call it GY. Okay? Yeah. We will do that. We will do that, okay? Alright, so we can write our equilibrium equations now. Summation of forces. Summation of forces in the x direction equal to 0. We only have the x, right? So it means the x is going to be equal to 0. Summation of forces in the vertical direction equal to 0. What do we have? Minus 20. Minus 30. Plus dy. Plus gy. What else? Minus what? Which is 10 times? Okay, I'm going to put like this. 10 times 4, which is the area of this rectangular shape, right? Isn't it? And this is all we have. So this needs to be equal to 0 to be in equilibrium. And then the other equilibrium equation we need to use is summation of moments about any point you want. Which point do you think is a good point? Why? I think there is a better point. No. D. Look at D. Let's think a little bit. If you replace your distributed load with an equivalent force, that will be located in the centroid of this rectangle, right? Or of distance. And then that equivalent load will pass on point D, right? So the moment produced by this equivalent load about point D is 0. Also, these reactions, dy, dx, the moment produced about d is 0. So we save all the work related to getting the moment produced by the distributed load. We save the reactions as well. I think the best point is point D, in fact. But you can use any point. It's up to you, okay? So let's use point D here. So you tell me, what is the moment produced by these 20 kilonewtons about point D? So it's 20 times 3. Yeah. What is the moment produced by these 30 kilonewtons about point D? Minus, yeah, times 3 as well, right? And the only one we need to use now is this one. Yes?
I was going to ask why you treat it as negative or minus 30k. Oh, yeah.
Yeah, it's clockwise, yeah.
I thought that you did the same.
Yeah. So the moment produced by this gy about point D is anti-clockwise, right? So it's positive. The distance is 6 gy, right? And that's all we have, isn't it? Is this correct or not? So look, from this equation you get gy equal to how much is gy? 5 kilonewtons. If you replace 5 kilonewtons in this second equation, you get dy equal to how much? If you replace here gy equal to 5, you get dy from this equation, please. How much is that? 85? Yes. 85. So it means the support at D is getting most of the load in the beam, right? Support at G is getting only a little bit. Anyway, it doesn't matter. It is what it is. Let me just confirm. Yes, correct. Okay, very good. So we can now, in fact, continue our analysis. So I'm just going to copy this. Okay, so we now have, instead of this support, we have a force here of 85 kilonewtons. Okay, and in this support we have a force of 5 kilonewtons. So if we work like this now, we are able now to continue our analysis, and which our analysis was to get the shear force and bending moment equations between point D and E. So we need to cut our beam in this region between D and E and look at the left side again, right? And do the Freebody diagram of this part of the beam. So that's what I'm going to do. So we have 20. We have this. Okay, something like this. 10 kilonewtons per meters, and we have this 85, which is the reaction I need to include, of course. Okay, you are all following? And I need to have now the internal forces, so the shear force Vx and the bending moment mx. And of course my x coordinate starts at point A, which is this point, and goes all the way until it reaches the plane where we are cutting our beam. Okay? And now we will focus on this free body diagram to do our analysis. Again, summation of forces in the y direction needs to be equal to 0. Right? You tell me, please. Minus 20. Plus 85. Minus Vx. What else? Yeah, so let's put dimensions here. So this is 1. This is another 1, right? This one is 2. From here to here is 2. So this from here to here is going to be how much? X minus how much? 4. X minus 4, right? Yeah, but we also need to have another distance. Yeah, we will be there, okay? It doesn't matter. We need to have another distance, which is this total distance here. I'm going to do it here, from here to here. How much is this total distance here? X minus 2, right? Okay? Let me just move this a little bit. All right? We are going to need that distance for the distributed load. Yes?
Regarding your example about the x minus 4 part, wouldn't that be a bad idea? Because you'd have to calculate the moment between C and D and between D and X.
No, but that x minus 4 is going this x minus 4 is going to be for the moment produced by this 85. You need this distance, right? Right? And this x minus 2, you will need that distance for the distributed load. And this x minus 4, you will need that for the moment produced by this 85 about point X. Okay? So that's why you need to have that there. Is that okay? Yeah. All right, so we are still missing here for distributed load. I need to multiply this 10 by x minus 2. Yes. And that's all we have, right? So this needs to be equal to 0. And from this equation you get Vx is going to be equal to minus 10x plus 20 minus 5 plus 15, right? Is this correct or not?
85 minus.
Oh, so sorry, it's not correct, of course. Sorry?
You can divide the distributed load into two different parts.
You can.
It's now, and the other part.
But why do you do that? You have more work.
Yeah.
You can do if you want, but I don't see any benefit. That's what I mean, right? Because yeah, in this case you have this entire rectangle, right, for distributed load. So
yeah, I mean the unknown parts will be smaller, and I think that you could have more control of what's.
No, but then you will have to calculate 2 times the equivalent force, 1 for each part, and 2 times the moment, 1 for each part as well. You will have 2 times more work. I don't see any benefit, to be honest. But you can do. If you are more comfortable with that, it's okay. It's fine. All right, so I think so it's minus 10x, that is okay. So we have plus 65 plus 20, right? So plus 85, isn't this? Is correct now? Very good. And now, summation of moments about point X equal to 0. Let's start with the 20 kilonewtons moment produced by these 20 kilonewtons about point X. How much is it? 20 times x minus 1. Very well. 20 times x minus 1. Look, for this we need to get this distance from here to here, which is x minus 1, right? Isn't it? So very good. 20x minus 1. Now the moment produced by these 85 kilonewtons about point X minus 85 times what? X minus 4, yes. This distance here, right? X minus 4. Very good. And the only, of course, we have mx, and we only need now to focus on the moment produced by the distributed load. So again, we will replace that by an equivalent force, which we know it is 10 times x minus 2. This is my equivalent force at the centroid. So we need this distance here, from here to here, and this distance is x minus 2 over 2. Yes, that's it. Very good. X minus 2 over 2. X minus 4 was for these 85 kilonewtons. We are doing the distributed load. So, look, this from this point to this distance from here to here is x minus 2, right? We only want half of this for the moment, isn't it? Which is x minus 2 over 2. So very careful with this. So we have now the moment, which is then 10x minus 2 is the load, is the equivalent force. I need to multiply this equivalent force by x minus 2 over 2. So I'm going to put here x squared, not x squared, x minus 2 squared over 2. All right? So this is my bending moment, equal to 0 to be in equilibrium. And we can just now work a little bit this equation. We have mx is going to be equal to minus 5x minus 2 squared, right? Then we have minus 6 plus 65x. And then we have 85 at the end.
No. What comes from 65?
Yeah, is this minus 85x plus 20x makes 65, right? Isn't it? And now we have here 340, which is this times this. 340 minus 20, 320, isn't it? So minus 320. What about this? No, it's minus because I'm sending to the right hand side. So I need to change the signal, right? It looks okay to me. Anyway, let's copy these now to our diagrams. Yes, but then you need to subtract 20. Let's paste here. Transverse shear force, this is our equation between point D and E. So, point D is x equal to 4. So we have 45, isn't it? Positive. So we will have 45 positive here. Which makes sense. Look at this. At point D, our reaction dy is 85, right? So the difference at point D between minus 40 all the way to plus 45, that difference is 85, which is the reaction. Look, we have a reaction here. We have a reaction here which is 85, right? So this difference here needs to be equal to 85, which is equal to the reaction, which is true. So and then now the other point is point E, which is x equal to 6, which means we have minus 60 plus 85, which is plus 25. And then this is the equation of a line again. So we have 2 points. We can connect these 2 points with a line. And this is my distribution of my shear force. Okay. Now for the bending moment, we have this equation here. Copy. All right. So, if we replace x by 4, we have minus 20. So how much is that if I replace x by 4? Minus 80. So it is this point here, minus 80. We have this point here already, right? This point here. And now replace, please, here x by 6, which corresponds to point E. You get minus 10? So you get minus 10 here. So let's say is this point here. Minus 10. Right? And again, a quadratic equation, it's the equation of a parabola. The coefficient of x squared is negative. So you will have something like this. Right? And then this is going to be your, distribution of the bending moment between point D and E. All right, so the idea of this example is just to show you, if you use the method we are using now, is a lot of work, right? Isn't it? You know, we didn't finish yet. But the idea is on the second half of the lecture today, I'm going to introduce you a new method where we're going to see is very, very quick to solve this, okay? So that's the idea, but let's finish this first. Let's continue now to the other. Let me just copy this guy. All right, so cut here now. I need to cut in this section of my beam. Look at left side. Let's try to speed up this now a little bit. I'm going to look at left side, so this is going to be my free body diagram. $20. 10, right? And then we have here 85, and then right? And then you have again your shear force and bending moment. Okay? Of course, your x variable, again starting at point A. So A, B, C, D, E. So we are cutting now between point E and point F. Okay? Let's do it. Summation of forces in the y direction equal to 0. So I'm going to speed up this a little bit. So we have minus 20 plus 85 minus 10 times. Look at this. We are not cutting now the distributed load. Distributed load, the equivalent is going to be 10 times the width, which is 4. Right? And then we have minus Vx. This needs to be equal to 0 to be in equilibrium. So we have Vx equal to 65 minus 40 is 25, isn't it? Is correct? Summation of forces equal to, summation of moments equal to 0. So we have 20 x minus 1, right? Isn't it? We have now 85. So minus 85. X minus how much? So I need to have now, for this 85, I need to have this distance, which is x minus 4. Right? X minus 4, isn't it? Huh? So that's the distance I need to include here, x minus 4. And now my distributed load, I will replace it with, this is equivalent force, which is 40, right? Is 10 times 4, is the area of this rectangle. And is located at point D, right? Which is the centroid of my rectangle. So the distance I need is x minus 4, is the same, this same x minus 4 here now, right? Okay? So plus 40 times x minus 4. And then just mx plus mx. This needs to be equal to 0. So we get from this equation the bending moment mx. Now it's going to be linear, which is good. So we have 60x minus 85 is minus 25. I send to the right hand side, becomes plus 25x. Right? And then I have here minus 160 plus 340, which is 180, isn't it? Minus 20, 160. Minus 160, right? So much simple equations now. So I can now plot my diagrams for this interval again. Sorry? Okay, so 25 constant between point E and F is 25 and constant, so we have something like this. And now for the moment, we have this equation. So if I get the result at point E, I need to replace x by 6, which will be minus 10, which is this point here. We have already this point. And now point F, replace x by 7, and then you get how much? Sorry? 15. 15, you said?
Yeah.
Positive, right? So we get 15 here somewhere. Equation of a line is just connect these 2 points with the line. So you have this little bit here. And then it starts growing over there. Okay? Yeah. And the last one we have to do is let me delete this. The last one we need to do is cutting in this section here and looking at everything on the left side. Okay? Or you can look at the right side. In this case, it's much easier, right? So the colleague here is asking, why don't we look at the right side this time? We can do that. Let's do this way. So if I cut then this and look at the right side, I will get something like this. So this is going to be my point G, where I will have 5 kilonewtons here, my reaction, isn't it? 5 kilonewtons. And then I will have my internal forces now. Look, now we are looking at the right side of the beam, answering your question. Your Vx now needs to go upwards. Okay? Your Vx needs to go upwards now. And your Mx needs to be clockwise. Okay? And, careful with this now, your x variable starts now at point G and go to the left all the way until it gets the section plane cutting our beam. All right, so this is my free body diagram, and then again summation of forces in the y direction equal to 0. We obtain, look, Vx, isn't it? Plus 5 kilonewtons needs to be equal to 0, so it means Vx equal to minus 5, isn't it? And then we have, for the summation of moments equal to 0, we have minus mx, right? So we are calculating the moments about this point where we are cutting the beam. Okay, don't forget that. So we have minus mx plus 5x. Right? Look, this reaction in red, the moment about point x is going to be anti-clockwise. So it's plus, right? This needs to be equal to 0. So we get mx equal to 5x. Right? So, copy. Let's plot these diagrams now. So in this region here, we get a constant transverse shear force of minus 5. So something like this. Right? And for the bending moment, we get an equation which is 5x 5x. Don't forget that my x now is starting here, starting at point G and going this way, right? My x is starting at point G and going to the left. So point G corresponds, in these equations, corresponds x equal to 0, right? You agree? So, if I want to get the moment at point G, I replace x by 0, then I get a bending moment of 0, which is this point. If I want the bending moment at point F, this point F here, I need to replace x with 3. So if I replace here x with 3, I get bending moment 15, which is this point here, 15. This is the equation of a line again. So I have 2 points. I just connect these 2 points with the line. And then I get my final distribution, okay? All right, so we have everything. Look at this. This is going to be asked in your exam for sure to do something like this. All right?